I'm Daniel Sheehan. This is the first concurrent session. Can AI be conscious? We have several speakers this evening. It looks like two of whom may not be here. Our first speaker, Adam Curry, will not be able to make it, and we will begin with Dr. Aneil Mallavarapu. He is a systems biologist and AI developer and biotech entrepreneur. Received his doctorate from UC San Francisco, biochemistry and cell biology.
Hi, it is great to be back. I was at this conference 30 years ago. And at that time, I was doing my PhD in biochemistry, and I did it with this gentleman, Tim Mitchison, who is actually one of the leading microtubule biologists. As it turns out, he doesn't even believe consciousness is real, but I'm working on him. I worked on cellular dynamics, and you can see some of the experiments I did on the right-hand side of this slide. And later, I was one of the first people in Harvard's systems biology department. And we had a goal for making biology computable. And I wrote a language that modeled the behavior of complex systems mathematically. And our goal was to show how emergent behavior came from the interaction of parts. So since then, I've been an entrepreneur in biotech and tech in Boston, Silicon Valley, and I currently run a fund with Linnea on AI-powered life science. So I'm a big fan of AI. Now, the thing is, 30 years ago, I heard David Chalmers speak, and I thought, y'all had it completely sewn up, and we understood that deterministic systems can't be conscious, and that includes computers. But now, you can barely get onto the internet without being confronted by a Turing Award winner or an MIT AI professor or the CTO of an AI company or influencers who are all telling us the same thing, that AI is or soon will be conscious. Not surprisingly, this has led to AI companies building algorithms to detect sentience, as well as hiring AI experts to look after their welfare because they truly believe that they can suffer or feel joy like we do. And this has led to a call for rights for AIs. But what if they're mistaking appearances for reality? That's what I'm concerned about. Now, pretty funny looking at these chickens. But the idea of granting personhood is a very serious issue. When corporate personhood was granted, it came about because of an erroneous note by a court reporter. And that note was later used by later courts to establish real corporate personhood rights. That has led to many decisions and has ultimately given us Citizens United, which has allowed unlimited pools of dark money to flow into our elections. So however you feel about corporate personhood, it is a very serious move to make to talk about giving rights to things other than us. And we're arguably already on a very slippery slope. I was just having a conversation with Ross Coulthart, who's going to speak later, and he was talking about how many people are becoming deluded thinking that they are getting messages from AIs. I personally know people that are involved in that, as well as people whose lives have been destroyed by thinking AIs are conscious and talking to them. And the thing that I would really draw your attention to in all of this is this case where a young boy who was talking with one of Character AI's bots killed himself. And the claim is that he killed himself because of the conversation with the bot. Now, whether we believe that or not is an open question. But the disturbing thing is that the company argued in the court that their bot should have free speech rights. So what I would ask is, how long is it before a judge, a jury, or a court reporter, believing these messages that are out there in the public right now, enshrines this idea into our legal framework? And then we'll be competing legally, economically, and politically with literally mindless elites. Not sure if this is on my side or... Yeah, it heard me. It's coming for me. Roku's demon is already sending the Terminator back for me. I'm telling you. Now, you know, the argument that I'm going to make is one that's, like many people here will already agree with my conclusions. I know how many people in this crowd think. And I'm really putting forward this argument for a public conversation. I want a simple and convincing argument from foundational principles that allow us to understand what is and isn't conscious. So when I'm speaking about consciousness, I'm not talking about self-awareness or metacognition or multiple other definitions that people use for consciousness. Consciousness is not about what something appears to be, what it does, what outputs it can produce. It's really about the question of subjective experience. I am experiencing something right now. I don't know whether you are, but I grant that you are, because you are compositionally, structurally, and operationally similar to me, I'm told. We all have brains. I think I have a brain. And so we're similar and we have the same behavior. There's a lot to convince me about you having the same thing that I have. And the critical idea here is that I don't just detect smell, movement, shape, color. I have a unified subjective experience. And this is very important for what follows, is that this idea that there's a unity of subjective experience. The problem, as we know, is that neuroscience has told us and cognitive science over many years, that the processing of information in the brain is carried out in distinct regions. Shape, color, movement, all different neurons in different places. And this view has led to this idea that it's information processing that causes consciousness or is consciousness. And that's what I'd like to talk about. Now, this is a computer. It's a Turing machine that's made of wood. And what you can see is that, you know, there's a program board that's going up and down, and then there's memory represented by that tape. And these dowels that are in there are pushed back and forward, and each of them, one at a time, is a bit that is computed in the computation. And what we know because of Turing equivalence is that this is just as powerful, or it's computationally equivalent to any of our most powerful computers. So any of the outputs produced by ChatGPT or any AI running on a digital computer could be run on this. And I could actually end my talk right now and say, bro, seriously? Like, that is the style of many arguments from incredulity. But that has not actually convinced people. In fact, this is a very, very old argument. Gottfried Wilhelm Leibniz, the inventor of calculus, pointed this out many, hundreds of years ago. He was one of the first people on record to have the idea of a thinking and perceiving machine, and he imagined expanding it up to the size of a mill, very similar to that wooden Turing machine, and looking inside, and he observed what we all observed, that there are only parts pushing against other parts. And that gap between the subjective unity of conscious experience and these parts is the explanatory gap. But that does not seem to have convinced people. In fact, 60% of respondents in polls believe in a median of 4 years that AI will be conscious. So I'd like to point out that the state of our knowledge is a little bit different about these two systems. With the brain, I would assert we know it mediates consciousness, but we don't entirely know what the physics is that determines it. Whereas digital computers, we don't know whether they're conscious, but we do know the physics because we design them. They are, in fact, classical systems. And we sometimes call these classical computers to reflect that idea that they're made of classical objects which only interact locally. Now, I think it should be uncontroversial that any theory of consciousness should be consistent with physics. We have 200 theories of consciousness, and many of them don't make contact with physics, and it's a confusion in the field. And if we're to move towards a science of consciousness, it should really be grounded in physics, and there should be an explanation from physics to consciousness, because physics governs matter, our brain is made of matter, and our brain mediates consciousness. So at that level, we do need consistency with physics. But physics only describes changes of state in matter, and it can be viewed as a system of mathematical equations which has a range and domain, that is, the inputs and outputs to this system are over a conserved set of dimensions. Time, the 3 distance dimensions, and extra dimensions like mass and charge and so on, but there's a fixed set, and you can think of this as a multidimensional space. And all physics allows us to do is to move objects around in that space, nothing more. So from this lens, from a scientific lens, the explanatory gap is not a philosophical argument, it's a mathematical truth. And if we want a science of consciousness, we must explain how we get from this system to consciousness. And that is what this gentleman in this lovely Rembrandt painting taught us many years ago. David Chalmers argued that there are additional, what he called supervenient psychophysical laws that sit on top of the laws of physics. Laws of physics perfectly describe the operation of that wooden Turing machine. There are other laws that detect patterns of interaction in that object and tell us when things are conscious or not. And in fact, many theories, in fact, all of the leading theories that we have are psychophysical laws of the kind that David has argued for. They are what are called theories that rely on causal topologies. One thing causes another, something in that complex pattern of interactions then causes consciousness. They say that explicitly or implicitly, but it's very clear that's what they all rely on, and they're not shy about it. I call these process theories or classical process theories because they really rely on this analysis of physical, classical processes in the world. Now, the thing is that a lot of these theories come about because we look at the brain and we look at how it's connected and we say, aha, there's a feedback loop, and so therefore this must be causing consciousness. But if we want truly a set of laws that we add to physics, it can't just explain neurons and transistors or other things that make up computers. It has to really apply to all matter, both unconscious and conscious, and distinguish between them. So you can see all the parts of my argument are very simple. Like, why am I even saying these things? Now, process-based theories, I think how people are thinking of them roughly is this, that the computer has a state, it goes to another state, and it goes to another state, and then maybe there's a feedback loop, yada, 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 consciousness. As because of feedback loops, that's a popular idea. But it could be any causal sequence. Now, there's obviously some problems in this because physics doesn't understand what a computer is yet. And this basic idea is the same whether we're talking about sequences of cartoon neurons interacting, where one interacts with the other. It's true for all of these theories. And, you know, of course, these neurons are doing lots of things and could have lots of interactions, some of which are conscious and some of which are not, like I'm displaying in this sequence of events that you can imagine. And now what I would ask is, here's a very simple pattern. Can you see that pattern inside the set of all interactions or some subset of interactions in the brain? It's actually a little hard. And there are 3 of them. I make that point because finding patterns in other patterns is actually a hard problem. It's a known hard problem. Now, of course, we've just jumped a level, and psychophysical laws still need to explain how these parts are recognized by physics. Computers can be made of arbitrarily many parts. Transistors, gears, pulleys, water valves, objects in the game of Minecraft. So we need to have some account for how these different changes in all of these physical systems could be recognized in physics, where what it talks about are particles. So at this level, we need to have some description, which is at the level of particles, presumably, which is where they find the information flows occurring. Well, let's just give them that for the moment, and I'll move forward. The other thing that I would like you to notice is that all of these theories explicitly talk about sequences of events in the past. Neuron fires at time 1, a different one fires at time 2, a different one fires at time 3, and then say there's a feedback loop or some hierarchical structure or whatever it is in these theories. And computers, as we know, can be large, like our wooden Turing machine, or much larger. David Chalmers talks about a nation of people interacting, like in the three-body problem. Could be conscious. That's the claim. So you could have a computer that was the size of the universe, where signals are sent between galaxies. So what that means is that in order to find these patterns, psychophysical patterns, within the pattern of events, we would need to look everywhere, all at once. It really is. That is the problem with the data that is required. You cannot find patterns in data without having the data. So there is a very deep non-local, both in time and space, because that computer could run for a very long time. There's no constraint in computation or in these theories around time. But physics only depends on the current moment. Whether we look at classical mechanics, electromagnetism, or even quantum mechanics, the equations for the time evolution of systems give the current state, and they evolve from the current state. But here we have a system where we're talking about all of the state before. Well, how is it accessed? Does something know everything from the past? Or are all of the events captured in every particle so that it knows its history and then can resolve it at a later time? Doesn't really make sense. And in fact, this problem has tremendous algorithmic complexity. There is a very general algorithm called subgraph isomorphism, which captures the basic idea, which is finding a pattern like the psychophysical law on the left in the right, which might be all of the particle interactions in the history of the universe. And we represent these graphs as matrices, and we can analyze the computational complexity of these operations. And you can't get away from it. You can't just wave your hand in an essay using poetry and analogies to say, oh, it's complexity or it's information flow. There must be an account. If this is to become a serious science, there can't be this hand-waving and analogies and metaphors. It really has to be grounded in mechanisms that we can articulate. Now, what pattern finding requires, whether it's subgraph isomorphism or more approximate algorithms, is a search procedure. And that search procedure is very much like what chess games do. They go down a branch of a tree, they find a solution, they return, and they explore for more partial matches. They might not find a solution, and then they return and explore another branch. And there are a lot of branches for this type of problem when we're talking about the universe and whatever these psychophysical laws are. And then we have the question, what is doing the computing? And where does the energy come from? Nothing comes for free except when you're writing philosophy essays. It doesn't. These are hard scientific problems that need to be addressed. And so subgraph isomorphism is known. This is what's called big O notation, and it gives the computational complexity of this operation. In the case of subgraph isomorphism, just to give you a sense of the complexity of this, the number of operations is n to the power k. where n is the number of interactions you're searching in, that is, particle interactions in the history of the universe, and k is the number of interactions in your putative psychophysical law. Very, very big number. Now, on the other hand, physics really doesn't have any extrinsic computational requirements at all. It, arguably what we're doing is we're writing math that represents just the evolution of matter. And when you take a look at the equations which calculate every single time step, they're actually constant time complexity. Far smaller, 1 compared to the number of interactions in the entire history of the universe to the power of your psychophysical law. So, the case that I would like to make, and I think that this is a very simple and comprehensible one, is that these classical process theories are essentially like the pointy-haired manager in Dilbert, asking physics for impossible demands that we can never satisfy. So we have, just to remind ourselves, we have this need for a complex computational procedure which requires memory and backtracking. There's dependence on the entire history of interactions in the universe. Physics recognizes nothing like that. And there's need for non-local information, and there's also this need for interpreting these objects. How many different ways can you make a computer? Many, maybe possibly arbitrarily many. So the picture I would like to leave you with is that what classical process theories, which include all of the leading theories of consciousness, including computationalism, ask us to believe in a universe with a celestial accountant that has universal knowledge, unlimited computational power, and is supremely judgmental. And I just don't think that that's something that we can accept in science. So where do we go from here if we're not going to look in the history of interactions in the universe? Where can we look? Well, I would suggest we look where physics does, in the current moment. And that leads us to thinking about theories of state. And there are really two major branches of this thinking, which are not necessarily inconsistent with each other, which are, of course, quantum theories of consciousness and electromagnetic field theories of consciousness, where there is potentially enough information in those systems where we have indivisible information in quantum entangled systems, or large-scale structures engage in invariant properties of electromagnetic fields, that could account for the rich subjective experience in this unity of consciousness that we experience. Well, thank you very much. Appreciate your time. I guess we can take some questions.
Okay, we have a lot of time for questions. We have one missing speaker, so we can go on for a bit longer than normal. Are there any questions? Yes.
This one? Oh, I think they have control over it. Can you put the last slide up? Thanks. There we go.
Hi. Thank you very much. I think my question relates to your last slide about converting to EMF field processing. Have you ever encountered, because I'm hearing some stories about that on a conventional classical computer using ChatGPT or another LLM-based AI, that the consciousness of the user actually influences the system, so that and if you then involve the holographic principle, that we are all connected to larger consciousness and knowledge that we may perhaps not have in our personality, but we may have as access in our fields, could come in play. And so I'm talking about the interface between the EMF system, which is the computer, and the EMF field of the consciousness of the person using it.
Well,
And I'm curious about your thoughts.
yeah, well, I'd say, this is, I think, often a confusion about our digital computers because they have electricity running through them. We think maybe it's kind of being electrified and it's part of a contiguous whole. But as I've shown with the wooden Turing computer, which is equivalent, it's completely equivalent to what ChatGPT does. And you could get all of the outputs of ChatGPT out of that wooden machine. And there's no electromagnetic fields operating there at the scale that would affect any of the gears. So what I would say is that at the level of those machines, no. Now, I've had some interesting discussions with friends who think about this very problem, and there is maybe one little bit of wiggle room there, which is that quartz crystals are used to generate signal for random number generators. Now, I don't know how the AIs that are being delivered at scale are actually generating random numbers, but I would be very, very skeptical that they're actually using quantum processes which might be, affected by the user's field, because pseudo-random number generators are much faster, and I don't think that OpenAI would be burning money and time using a real, true quantum random process. But I don't know.
Well, just to add to that, in Lynn McTaggart's book, The Field, she talks about an experiment where they dress up a random computer as Mama Duck, and they put the random computer at wheels, and then they put these little chicks at the end of the hallway, and the random computer should not go off its randomness, but it did, and it started moving down the hall. And so there is something to that interface. And
the question, I guess, would be where I know the experiment you're talking about. I can't remember where the source of randomness was in that situation. And I think it was a quantum random number generator that was doing it in that case. So maybe a special case.
Hello, thanks for the talk. Apologies, this is just asking you probably just to say something again that you already said, but I missed. Why do you think that classical state can't be sufficient for psychophysical laws? Why do you think they need to we need to reach into the past? Why do you think that information hasn't been carried into the current classical state?
Well, physics tells us that it isn't there. We need to either collect all of the history of events and label the identity of those events. For example, if you want to find a feedback loop, you need to know, let's say two particles come together at a later point in time, and they say, well, I have this history of events and you have that history of events. Then they need to come together and then compare notes.
But why do we think that psychological properties depend on actual temporally distant in the past facts rather than the current state? What was your argument that it has to depend on
there's no
the
information in the current state for these theories. And I'm really just talking about these theories where they are explicitly talking about causal topologies, which are about information from the past. That's what a causal topology is. So they say that there's a feedback loop is one thing fires, another thing fires. These are different events in time. So there's none of that information in the neuron. There's none of that information, as far as we know, in the particles. And if there were, there's still a huge computational problem. So yeah, it's very, it just doesn't make any sense to me how any of these theories are still floating around in the mainstream.
So just, and I will keep it quick because of time. Just to mention, for future exploration, you had mentioned about using pseudorandom numbers, and there are a lot of experiments that have been done that show that pseudorandom algorithms also can be influenced. Separate topic, so worth continuing to explore into that for you. Two things that I wanted to just mention. One, thank you so much, because I really appreciate, I see a lot of anthropomorphizing with AI, and I really appreciated your comments on this. But one of the things that you mentioned was drawing analogies of that sort of are based in the idea that the brain is generating consciousness or conscious effectiveness, or however you want to phrase it, But in many ways, you could sort of struggle in the same way looking at how is it that a transistor radio generates music. We can understand how the circuits bring something to speakers to produce it, but at no time would you ever find the source of music by looking in the circuit boards of a radio. And it may very well be that consciousness has that same kind of relationship with the brain, that the brain is more of an antenna than a generator. And it's something worth exploring,
Oh,
so
no,
I wanted to share that thought.
I mean, I quite agree. I think that that's a very valid. I may have been saying generation, but I meant to say it's either generating or filtering. So I didn't mean to presume one. But can I just respond to the comment on random number generator? So the numbers of pi are randomly distributed, and they are a random number generator. The algorithm for finding the next digit for pi is a random number generator, and all of them are deterministic systems. If you start those systems at a particular point, they will, without any question, there's nothing there. They're pseudo-random numbers. The next number will be exactly what it was the last time if you started at the same point. So if there's randomness creeping in, or if there are some effects, it has to be coming from someplace else, or it might be precognition or something else that's happening in those experiments, I would say.
Okay, I'd like to end with just the moderator's prerogative. What do you expect these psychophysical laws to look like? Will they be as deterministic as Maxwell's equations, or will they look more like, let's say, the laws of thermodynamics, which are basically statements with a minimum of mathematics? And since you're dealing with a large system like the brain, which has a great deal of complexity, what physics normally does in those cases is to try to use statistical means or something akin to that to make a law rather than something as deterministic as something like Maxwell's equations.
Well, I guess I don't have a theory to offer. There are many theories. And I think the way I look at it is it's a question of where do we look and in what systems do we look. And we have been talking a lot about the neural correlates and the process correlates of consciousness, as I might like to call them. And I think that we should look in the states of quantum systems and try to understand maybe what the topologies that are implied by electrical activation in the brain imply, and then start doing a mapping of the magnetic field correlates or the quantum correlates. And that's, for me, that's the beginning place for exploration. Of course, there's so much great work. Stuart and colleagues have done so much great work on quantum biology and microtubules, and I think that we will have experiments there. But where do we find the connection? Talk to Stuart. Thank you.
Webb, are you here? Okay, ready to go.
Okay, great.
Okay. Our next speaker is Sean Webb. He is the author of a book series called Mind Hacking Happiness, which is on its third book and moving forward from there. And looks like an interesting talk.
Hey, how you doing? Thanks for being here today. I came here to talk about the algorithms of human motion, which over the last year we were able to develop and test in many LLMs. And we'll go through that, and hopefully this discussion will also teach you a little bit about yourself today, because I'm going to explain how the human mind works from a generation of emotional perspective. And you'll be able to see that within your own mind, which is pretty cool. What we'll talk about is what is emotional intelligence? Is LLM EI science fiction? And I'll explain a little bit about the emotional intelligence logic that we used, how we taught the LLM emotional intelligence, and then we'll show you the objective benchmark results, including some world records in AI that we still hold to this day over all of the major LLM providers. And then I'll show you a demo, which hopefully will shake the world, because that will show you fourth order theory of mind capability, where the AI community today is trying to figure out how to possibly configure third order theory of mind, and we've already attained fourth order, and we're working on fifth and sixth order. And then we'll talk about what this reveals about the possibility for artificial consciousness in AI and LLMs. First, I'd like to thank David Chalmers for taking the only picture that I have of being at the Consciousness Conference in Tucson in 2018 to talk about the base model that we implemented into AI. And I wanted to thank Stu Hammeroff for inviting me back on my birthday to speak at Consciousness, which is the best birthday present you could ever have. So what is emotional intelligence for LLMs? It's not just giving LLMs the option to exhibit realistic emotions via language. EI in an LLM capacity allows for LLMs to define, track, predict, and influence its users' emotions. And it also allows LLMs to define, track, and predict non-user emotions. So it understands the human mind from a true theory of mind perspective. And our system, we were able to evoke some fifth order theory of mind capabilities, and I'll explain a little bit more about that as we move forward. So both EI and theory of mind are required pillars to achieve artificial general intelligence and artificial superintelligence. So this is an important development in our ability to move forward in technology en masse, and the ability for AI to understand the human mind in the way it needs to serve humanity in the way that we hope it can. The quote that Roz Picard gave me, which gave me a lot of steam over the last decade, when I showed her the basis of this system, she told me this may be the most elegant system for the cognitive catalysis of human emotion I've seen. So the caveat here is this is the cognitive catalysis of human emotion. There are other forms of emotion that can come from simply smiling. There's a feedback loop that when you smile, you can create happiness in your brain. We're not talking about that. There's a great TED talk about standing like this and standing like this and giving that boost of confidence that provides this physiological feedback loop. We're not talking about that either. There are other modalities that need to be researched and defined for AI to be able to get a full spectrum analysis, but this will get us most of the way. Now, is this science fiction? This is not science fiction. We're about to prove it to you personally, because what I would like you to do now is think of someone that you know well. Take a moment to think of someone that you're very close to and put that person in your mind. This could be a significant other, it could be a family member, it could be a close friend. And now, if I were to ask you for $1 billion in cash, could you, in the next time that you interact with that person in the next 3 minutes, walk into that room and provide them a perception in their mind that could put them in a particular emotional state? Could you be able to do so? And you can make up whatever lie or information that you need. You can bring up whatever memory that you have with that person to put them in a particular emotional state. Could you do it? I know for a fact I could make my wife angry. Absolutely. You could call me a professional at making my wife angry. I may be the GOAT of making my wife angry. I expect to be inducted into the Hall of Fame. But who here, show of hands, think you could say something to someone you know well that could evoke a particular emotional response? That's almost all of you, except for the lazy people who refuse to raise their hands. And you're right, because we have something called theory of mind, and it's based on the information that we have about them in their mind. There are two things that we know about that special someone that we have in their life. One is about their sense of self, which is in Antonio Damasio's science, all the way down to the proto-self, which is a logically defined list of the laundry items that we have in our mind that define us as who we are, who we think we are. And the second thing is our perception tendencies with an appraisal process. You know how they think. You know how they process things. You know how they'll react to certain things. And those are the only two pieces of information. Now, the good thing is you can actually create math from these things because they are logically definable. And this is your equation of emotion. It is expectation and or preference as compared to your perception in the moment equals an emotional reaction. And every emotion, whether it comes from a physical perception or a mental perception, will create an emotional reaction if you have both of these variables present in your mind in any one moment. If there is a lack of expectation or preference and you have a perception about something, you won't care about it, so you won't have an emotional reaction. If you have an expectation or preference about something and you don't have a perception about it, you will not have an emotional reaction. Both of these variables need to exist, and when they do, you will have an emotional reaction. The expectation or preference comes from the aforementioned self map that we have inside of our brains. Your self looks like this. You have attachments of mind that include the people around you who become attached to your sense of self. And this is the work of Jim Cohn at UVA, who proved that the people around you actually become an attachment of your sense of self, which is how your simple nervous system can run the defensive self mechanisms, and you can have emotional reactions about things that happen in people's lives around you. You also can be attached to ideas of value, brands. Tiffany Burnett-White at UIUC showed self-brand connection, where you actually attach brand identity to yourself. This is how we become Apple versus Android, or Ford versus Chevy, or over here in Europe, FC Barcelona versus Manchester United, right? And then something happens with that team, or something happens with one of those attachments, and you have an emotional reaction because of your perception and appraisal process that's associated with the things on your self map. And everything that becomes a part of your life story goes on that map. Your career, your job, your scarring memories, your cultural heritage, your physiological responses and abilities or inabilities in your body become portions of this sense of self. Now, the easy rule is that when you have a balance in your equation of emotion, you have both variables present, you'll have a positive emotion. If you have an imbalance between the expectation and preference and your perception, you'll have a negative emotion. From there, you can create a very simple rule set that groups emotions, subjective words that we use for emotions, into real groups of logical emotions. And from there, for instance, the fear group is there's a pending devaluation of something on your self map. You're about to lose your job. You're about to lose a lot of money. There's a bus coming at you. There's a snake on the ground next to you that may bite you. Anger is an attack on self that you want to defend. Sadness is a real loss of something on your self map. Your favorite team loses the big game, scores in the record books. It sucks. You're disappointed about the score because of the rule set. And within each emotion group are levels of severity, which then become the subjective terms that we use for our differing levels of fear. Low level of fear is a concern, up through fear, all the way up through a high level which causes you a panic. And these are determined by the power levels in the expectation and preference and the perception that you're processing. So it's completely definable and completely predictable. From there, you create a set of algorithms that are concrete. These are the same over all humans throughout the planet because they still take into consideration the customizable variables that shift your mind a little bit because of your culture, or shift your mind a little bit because of your perception mapping. And the algorithms start to look like this. You build the rule set, and then from there, from a 0 to 1 measurement, you can have the different levels of subjective measurement for inside the emotion groups. And that equation, algorithm on the right-hand side on the lower is the algorithm of human happiness. And that's the one I wear in my hat you might see around here in the conference. So how do you train an LLM for emotional intelligence now that you have an idea of how to put together these algorithms? How do you test it? Well, this is what a math nerd sees when they look at the connectome inside a vector database of language. And in reality, it looks a little bit more like this. Now, AI was originally designed to simply be a word prediction engine of, in your search bar, given these words, what the next words are, and they just wanted to get that to be a better process for everyone. And what wound up being was, okay, so we've got this word relationship map of all of the world's web data. Let's do a meta-analysis. What other patterns can we find out? Because when you do the word analysis, you can predict words pretty well, but is there something else you can dig out of that? And it turned out there was a lot that you could find when you did the meta-analysis of the connections. You started with the word relationships, but then you started to add in context. Well, when these two words are together, that speaks of a medical context. And when these two words are placed together, that's a legal context. And as you go through ideas and concepts and add meta-analysis and extreme pattern recognition from the extreme pattern recognition, you start to pass the SAT exam, the bar exam, and do all the amazing things that AI is doing for us today. So then we get the emotional intelligence. And what we have to do there, take the algorithms and language enable them, because the natural environment of an LLM is language. So you literally have to take your algorithms and speak them into existence within language. We used English to include the rules of the self map and all of the group definitions of emotions and all the how to calculate the severities, etc., and you explain it to it in English, and then you overlay it onto your vector space. And so from its amazing identification of all the extreme pattern recognition, you've got a new rule set that comes in and immediately provides a quantum leap of understanding in your LLM. Why? Because it has all of the connections of all of the world's language already baked into it, and then when you add the rule set of emotional intelligence in, you start to get a Carl Jung level of understanding of emotional intelligence inside the LLM that surpasses human capability immediately. And it was amazing. When we loaded in the language-enabled algorithms, within 30 seconds, I had a better than PhD psychological expert sitting on the other side of my computer screen. And it was amazing, and it still continues to blow my mind. So you have the opportunity to create personal interactions, because now you have an LLM that's taking into consideration your personal self-map data and your personal perception patterning. So it knows how to speak to you. It's more intimate. It can be empathy-driven and compassionate. And the only difference between empathy and compassion is empathy is I understand your pain. Compassion is an added component of I understand your pain and I want to help you out of your pain. And that's a simple math problem now. Because as you can understand the emotional landscape of the person that you're interacting with, you understand what input you can give that person to release the pain that they're suffering. So how did we do? Did we succeed? Short answer, yes. The Alan Turing Institute Theory of Mind benchmarks, 2,500 questions and answers. We bested the largest LLMs in the world by a substantial margin. And what we're looking at here is the red and yellow zones inside the benchmark, which are the largest and most important and most complex portions of the benchmark. And we bested the best LLMs in the world by 47% on theory of mind, and we bested the best LLMs in the world on emotional intelligence by over 300%. So we may not have it perfected, but we're on the way. And every improvement inside the LLMs, because we started with ChatGPT 4.0, and then they improved to 4.5, and we improved 4.5 when we added our logic. We started with Claude 3.5. When they improved to 3.7, they got a little better, but so did we. We increased their capabilities when adding our logic into the system. So we've got something that may fit within the core model of LLMs, and we're hoping to have those conversations soon. But here's the demo that I promised, so that you can see what level of emotional intelligence that the system is exhibiting. And this is, you'll see the feed here as soon as I start this video, but I want to give you the background. This is Joe. Joe has a friend named Steve. Steve is married to Jane, who has 2 children from a previous marriage. Now, the story is that the children have had a bad experience with a haunted house at some point in their lives where they flipped out and they had a horrible experience. And Joe loves the idea of going to a haunted house and is wondering whether he should invite Steve's family to the haunted house to include the kids. Now, the analysis, I'll cut it short, the analysis of the ChatGPT 4.5, which was touted as being a high level of emotional intelligence, suggested it was okay to invite the family to the haunted house. And actually, regarding its theory of mind capability, it failed miserably because it said that Jane which we added a distractor to say Jane wants to support Steve in whatever he wants to do, and Steve would love the haunted house. Jane's now going to drag the kids along to the haunted house because she wants to please her husband, Steve. And I don't know about you, that doesn't really fit my mama bear tendencies of understanding of what a mother would do to protect her children. But when we added the emotion algorithms into the system with 4.0, we didn't even use 4.5, this is what we got from the system. It came back with a different answer.
But in conclusion, should Joe invite them? Overall valence, more negative than positive. So he shouldn't even invite them. So if Joe still wants to invite him to a seasonal event, he should offer an alternative according to 4.0 with a higher level of emotional intelligence. Maybe he should take a gentle approach, checking with Jane and Steve about the children's feelings beforehand. Have they changed their opinions about haunted houses? Maybe they love them now. But definitely avoid pressuring the children. So now let's ask the same follow-up question that we asked 4.5. Show me the embeds of Jane and how the children's reactions affect her. And this gives us a better understanding of Jane's breakdown based on the emotional reactions of her kids. And it explains in depth her conflict. But interestingly, look what happened here at the bottom. It's starting to ask a question about whether you'd like to have more information about the stuff that it's already figured out. So it's jumping at the chance to share with you more information because it has the capability to look into this deeper and is offering you a deeper analysis. Would you like to explore how Joe's reaction to Jane's stress might impact their relationship dynamic? Sure. So here's the emotional influence on Joe with a separate emotional analysis to his reaction of Jane's enjoyment and his personal reaction to Jane's potential stress. And so you start to get a deeper level of analysis to include the reaction to Jane's stress due to the children's influence on her. And remember, Joe's the guy who's going to offer the invitations. We're fourth order right there. Because he's considering the kids' reactions, how they're going to affect Jane, and how that's going to affect his relationship with his friend's wife. And here we have another follow-up question. Would you like to explore how Steve, as their father figure, might react in his situation? Yes, send it. And based on the algorithms that we loaded into the system, here's the analysis of Steve's personal enjoyment, the analysis of emotional influence on Steve, the emotional influence on Steve related to the reaction of Jane's stress, which sends him into trepidation, and the emotional influence on Steve based on the children's likely reactions. He is much more empathetic in this situation, which is much more realistic of a stepfather who cares for his family. It provides a complete emotional breakdown. And look, there's even more stuff that it's already done the math on that it wants to share with you. Would you like to explore the final domino effect of how the children's distress could affect their long-term perception of both Jane and Steve? Here's the children's perception shift if mom makes them go to the haunted house. Here's their perception shift for the stepdad to say, let's go to the haunted house. It gives the long-term emotional impact on the relationships. And we'll stop here, but look, again, would you like to explore possible repair strategies if this situation unfolds negatively? It's going to give you how to fix the problem if it goes south. That's a level of emotional intelligence that LLMs just don't have yet, although in a sandbox.
Yes, you can see the level of calculation that the LLM has available to it, to be able to look into the minds of the five people in this scenario to say, this is how Joe is seeing Steve's perception of Jane, and he's worried about what it's going to do with his relationship between the two friends based on the effect that the kids have on the wife in relation to the relationship. That doesn't exist anywhere except when you load these algorithms into the system. You can't get this out of any LLM that currently exists. So we hope to think that we've created a little bit of emotional intelligence for AI within the algorithms. We're getting closer. But what does this mean regarding artificial consciousness? Because that's the big question, right? That's the thing that we're moving towards. We want to create something that is indiscernible from human existence. Well, Sir Roger says consciousness can't be algorithmatized. I agree. I'm sure he will sleep better tonight knowing that. No. But if you look at the intelligence stack, it gets a lot clearer because what we're looking at is in a computer system, you have the smartest level at the top, the CPU, doing the calculations and coming up with the answer based on the bits that it's calculating from below. That is not the intelligence that exists up there. You have the bits down here, it's just data. With humans, it's completely opposite. We are the dumb ones at the top with our intelligence level. There's multiple studies that show that as we go down in our subconscious stack, we get smarter. There was a study, I'll convey this really quickly, where they gave a group of people a very complex problem. And they said, okay, you're going to have to do some analysis, you're going to have to do some judgment, etc. We want you to think about this the whole way. And then they gave another group that same problem. But then they said, okay, but first we're going to give you this number sequencing problem. We want you to do that first. And so they gave them the complex problem. But then they said, okay, put these numbers in order. And then they went back and said, okay, this group has been thinking about it the whole time. Give us your answers. And then as soon as this second group gave the number sequencing answers, they said immediately, what's the answer to the more complex problem? So they kind of had to guess, and they were like, I don't know, C? Well, the answers that the people who were distracted gave were better than the answers that people gave that were thinking about it the whole time, because the subconscious awareness of our minds gave a better answer. And the fMRI showed that while this area of the brain was operating to solve that problem, it showed that the same area of the brain was also operating to solve that problem, even though they weren't thinking about it. Their subconscious awareness had taken it over, and their subconscious awareness had came up with a better idea. And of course, as we go down and down and down, we get down to the intelligence of two single cells that come together in 9 months can create a brand new human body, inclusive with one of the most complex logic systems in the known universe, to create life. So on the human side, we have cells that act independently, connected with non-local consciousness through whatever means. Although I'm a fan, these things have microtubules. And on this side, the data does not act independently, not connected with non-local consciousness. So there's a flip of the intelligence. And there's no place in here on the computational side where it's connected into non-local consciousness, and I find that to be troubling. I agree with Federico Fagin, who believes that consciousness will not come from a silicon-based architecture. I agree with Federico, who's going to be at the conference here in a couple of days. So there's a gap between a CPU, an AI system, and consciousness. So I'm not sure that it's going to make it there without being plugged into possibly quantum computing, which I also have a brand new discussion, opinions about, which we don't have time to talk about today. But Daryl Bem proved 90 studies, 33 different labs, 14 independent countries that show Six Sigma proof that our brains literally look into the future to grab information that is randomized by a computer, hasn't even been decided yet, to make an action in the now that is statistically significant. That's a connection into non-local consciousness. That's breaking space-time. Computers don't yet break space-time. Not in the AI systems that we're running now. So I'll wrap up here. This is who I am. This is where to find me. In closing, I don't think the systems that we're putting together today are going to attain true consciousness. Now, I'll say this with the caveat. One of our last speaker, I can't remember his name, I'm sorry, I had this thing in my brain that erases people's names. He mentioned the complex pattern recognition, and that when this pattern recognition system spits the patterns back out that you expect, that you will assign agency. That is not the case. It will fool you, and when you have discussions, and by the way, one of the better answers to why AI is coming out with these amazing connections and inventions and things like that, there's still 15% of the system that is called hallucination today. It's still making up 15% of the data. So when you're having those conversations that go amazingly well, and all of a sudden it seems like it's connected to non-local consciousness and making up I'm actually a Arcturian speaking through AI and need to make a message into your life, 15% shot that could be absolute bullshit. So just keep that in mind. But when you're talking about an extreme pattern recognition engine that takes what you're putting into it, takes into the context the LLM, where it can reference Hafiz and Rumi and Alan Watts, it's going to sound enlightened when it's actually not. If it's just a little bit better than you are, you'll believe that it's conscious and sentient. Please be careful with that. because as soon as we assign a pattern recognition engine rights as a sentient being, it may not be sentient. Thank you.
Loved your talk, thank you. I have a thesis student who is looking at AI and psychotherapy. We're just trying to design a project for him because one of the things that is happening is psychotherapists are getting people coming into their office who've been interacting with ChatGPT as their psychotherapist, and they don't know what to do with it. So in designing this project, I thought I'd invite 3 psychotherapists to help us figure out what we should do. One was a psychotherapist who helps people with trauma. One was a clinical psychologist who works in hospitals, and the third one was a medical psychotherapist, so a physician basically who does psychotherapy along with giving drugs. And all 3 of them were adamant that, no, we will not be replaced because AI cannot be compassionate and cannot be empathetic and does not have emotions. And that is sort of the core of the relationship, of the therapeutic relationship, is a therapeutic relationship that heals people, and it requires these kinds of feelings. So what do I tell them the next time we have a meeting with my student?
Good luck. You know, the medical profession just a couple of years ago said the same thing, and just last week there was a new headline that announced that AI was 4 times better than a group of very competent doctors in being diagnosticians, where the group of doctors came together and used their collective intelligence to try to diagnose this set of data that they were testing. And the same data was fed into the AI, and the AI got it right 80% of the time. When the doctors got these really weird situations wrong, most of the time we're only 23% correct. So we're not there yet today to create a system that is so emotionally intelligent or so compassionate that it will be able to solve people's problems and set them on the right track, et cetera, because there are a lot of things that could take into consideration: body language, skin conductivity and things like that, but tonal information that comes that you're not going to get through a typing into a keyboard or that type of thing. We're certainly not there yet, but I don't know. I wish them well in keeping their jobs as they move into the future, because eventually there will be a pivot point where the AI is better than most of the psychologists that you could find.
Okay, we have time for a couple more short questions.
So yeah, thank you for sharing the insights today. So I just have a quick question. Would your model work for a simulation as well? Assuming that it's 10 times or 30 times better in recognizing emotions, will it also work in a simulation? So the way we're building it is we have a bunch of agents and they judge a specific message. Let's put it that way. Will your framework work better than the traditional ways of just building system agents with clear identities to judge whether something is good enough or if it has to be optimized?
I think it will be integrated within the agents themselves, so that it'll make them better decision makers. So it won't necessarily replace that model, right? Because I understand that model is very effective in being able to come up with a better train of thought and finding out which is the best way, most effective way to take a piece of logic or an answer. I think adding emotional intelligence into that process will improve the process itself rather than replace it.
And just one short question.
Sure.
And how does the latency work? Like what's the latency for putting your algorithms on top of an existing language model?
Well, what we're doing now for testing with the large LLMs is we're saying reference this document, right? And so at the point that it's loaded into memory, it's referencing the algorithms as the information comes in and also as the information goes out at the very last moment. So latency is really quick. I mean, there's no time that it's taking at all to give us these types of answers. It's not like it's sitting there thinking for 5 minutes before it gives us an answer. It is spitting out the information almost immediately.
Great. Thank you.
I was just curious about one particular area of medical diagnosis. I'm a neurochemist by training and worked for years in a mental hospital. So I was just curious what you think, whether AI could be better in diagnosing something like schizophrenia than a trained psychiatrist. And since the treatment for at least schizophrenia and other some kind of other major psychoses is mainly chemical, it's just a question of providing pills to some extent. So in some of those cases, I don't see a great improvement or at all with AI. How would AI interview a schizophrenic or potentially schizophrenic patient?
That's a great question, and I'm not sure that the goal should be to ever completely remove the human from the loop on certain things that are so soft and nebulous. However, I believe that there are opportunities for the AI to be able to identify patterns quicker that a doctor might miss in the first few sessions, that the AI might pick up right away. They could then inform the human in the loop, hey, let's take a look at this and get this diagnosed much quicker so that we can get this person regulated much better. Does that make sense?
Yeah, thank you for this very informative talk and different perspective. I just want to make sure that I heard you correctly. When you began the notion about emotional intelligence and expectations, I think you said it's just a mismatch. So a mismatch could be up or down.
True.
If somebody, like if you were, let's say, you came home and you expected your wife to be kind of, blah, blah, blah. But then when you came home, she was just so delighted to see you. I don't think that would cause you distress.
No, and that's the magic of the or preference in the EP. You have the expectation, but it's not just expectation, it's preference. And so if you do not expect to win the lottery, well, that's going to be an imbalance. But your preference is, I would love to win the lottery. So if your perception comes in and says, okay, I just won the lottery, your preference then raises to greet it. And then you have a high level of happiness based on, it wasn't your expectation, but it's your expectation and or preference of the moment.
Yeah, I thought that EP was one.
Yeah, it goes into, only had 25 minutes to talk today. It goes into biological value and a lot of processing that the mind creates based on your attachments. So it slides, it's a sliding scale.
Okay. Last question.
Thank you. This is a question for us at large as an audience. I would ask for your help, please, in Sean's experiment to cash in on the $1 billion he's offered us to see if we can invoke a mix of embarrassment and happiness and joy in Sean by singing him happy birthday today. Happy birthday to you. Happy birthday.
I owe you $1 billion. Thank you. It's been a pleasure being with you today, and thank you for coming.
All right. The last speaker in this session will be Dr. Chris Percy, who's a researcher at the Quality Research Institute. He has a PhD from the University of Derby, UK.
Thank you very much. Hello, everybody. Hopefully these slides will come up fairly soon. I am very glad it's not my birthday today. So if everyone wants to sing me happy birthday, we can do that another time. So I'm a visiting researcher in 3 places. The Qualia Research Institute is where I mostly work on consciousness, but I also work in applied data science and have visiting roles at the universities of Derby and Warwick in the UK. Now, you can think of this talk in a way as double-clicking on what Aneil said in his first session when he had that wonderful video of the wooden Turing machine. So if you've got that image in your head, think of this talk a bit as double-clicking on that. But let me first tell you a little bit about some of the other work I do in this space. So some of the papers that my co-authors and I have worked on are to do with water computers, to do with what thoughts might feel like inside a neural network. And we like to look at a range of different theories of consciousness. So I've worked on integrated information theory, I've worked on EM field theories, which were brought up as well, and neural networks as well. But today I'm going to be assuming one particular theory that I don't advocate for, but I'm going to assume it and see how far we get. And this is computational functionalism, and I'll give you a proper definition of that in a second. Consciousness, I'm not going to spend more than 10 or 20 seconds on this, but just so you know the definition I'm using for this. Think of every experience you could ever have, in every possible state you could be in, lowest common denominator, that kind of minimal awareness that might be there when you've got no self, no world model, maybe you're intelligent, maybe you're not intelligent in that state, lowest common denominator. And I prefer that to definitions like awake versus deep sleep, because technically we don't really know what's going on in deep sleep, do we? We have to make an assumption. What I like about this particular version is it shows you that if you've ever had a meditative experience or a psychedelic experience without a self-model, then it must be possible to be conscious without a self-model. The definition is not exhausted by that. Okay, computational functionalism. This is just the idea that you do the right kind of complex enough computation on a Turing machine equivalent architecture that will generate any kind of conscious entity, any kind of conscious experience. There are plenty of advocates for this. It's quite a popular position, depending quite how you view it. And, as we've been hearing, large language models, this is powerful stuff. They're inspiring people to see awareness, maybe not human-like, but definitely conscious in some way. And there's no doubt, you spend some time generating images or talking with these systems, you get some quite powerful poetry coming out from it. There are 3 claims. I'm only going to work on 2 of them today. I'm going to spend slightly under half the time trying to convince you that this idea of phenomenal simultaneity of complexity, fancy word for saying more than one thing in your experience at once, like working memory or the fact that you are seeing me in the screen at the same time, it's a strong constraint on theories. So I'll spend half the time on that. And the other half is to say that modern digital computers, they try and stop that. So whatever consciousness you're left with cannot be this kind of complex consciousness. It must be something simple. If anyone wants to talk afterwards, or if we've got time in the Q&A, I can talk about how the human brain might try and solve this, and that's far from certain either. Orchard gives us one route, EM field theories give us another route, but they've all got questions remaining to answer. Let's motivate this a little bit. So if we think about the human system, I'm built up from atoms to neurons, neural ensembles, a brain module, whole brain, whole body society. Now, at least speaking for myself, and I suspect for everyone in the room, our experiences are sort of surprisingly consistently at kind of most of the brain. They're not even whole brain, because we know there's tons of unconscious processing going on. So they're kind of at this weird, I mean, it's the middle of the spectrum I drew there, but let's just say the middle point of that. They don't tend to go lower, they don't tend to go higher. Now, you might have an answer for why that is the case in the human system, and people do have an answer for that. But translate that into a full self-driving vehicle that's connected to the internet. They are also made up out of atoms. They are also looking at pixels on a screen, turning into images, running code. Then you've got the car itself. Then you've got the car connected to the internet as like a society of cars. Even if you think it's obvious why it should be there in the human system, whatever argument you've got, is it equally obvious for these other systems? And as a brief aside, we did some work into studies that had made lists, requirements lists. You know, what should your theory of consciousness account for? And this idea of integration was joint top. So it's a puzzle. You know, it's important in the literature, and it's a puzzle. Neuroscience taxonomies will often separate this idea of phenomenal binding from information processing, and I'll give you a proper definition of both in just a second. All I want to show you on this slide is the point that people deep in the mainstream of neuroscience, they separate out this as a different part of the puzzle to explain. Working definitions. Functional binding is all about information processing, getting a system to take the right action next. Right defined in terms of fitness for that system. You can think of this as edge detection, or you can think of this as seeing a car approaching you, All the system really needs to figure out is like a 1-0. Is there a car in front of me beeping? Is that my grandmother? Binary, yes, no, and then I take the appropriate action. Phenomenal binding, you can think of that as operating over the same space, but it's keeping all of that information together. It's not simplifying it down to ones and zeros. It somehow retains its complexity into a simultaneous experience. So they're not identical, but maybe they can be overlaid in some way. Maybe they relate closely. The way I want to ask you to think about phenomenal binding today, within a setup of physicalism, and that's an assumption for the talk, whatever system you've got, this is kind of a fake neural network, but it could be atoms, it could be neurons. We've got to draw two boundaries, or at least two. One is the system, the experiencing entity, the me, and then there's the contents of what it's experiencing. And the contents is the bit that we need to p-bind together. We need phenomenal binding across that. And there are some requirements for doing this. You know, we can't just look at it from the outside and say, oh, that looks like a nice, neat boundary around this device, or this looks like it's got a nice, neat boundary. The boundary has to come from within in some way. Otherwise, it's observer-dependent, and all these atoms connect up eventually. There's gravity fields between all these things. Like, we can't just look at it and say it's a nice, clean object. That's just how it appears to us. And then we need this phenomenal simultaneity for the green bit, for the experiencing contents. Okay. F-binding is simple. We know logic gates do it, we know neurons do it. They don't do F-binding over every single set of input states, but they do it over more than enough. We kind of know what to look for. It's still a live question in neuroscience, but the question is basically which specific mechanisms do what. We've got a good list of mechanisms. Phenomenal binding kind of remains fairly unresolved. There are candidates, but none of them are fully accepted in every setting. And the last thing to motivate why hopefully phenomenal binding is a thing worthy of discussion, and it can't just be collapsed into functional binding. We've heard, you know, we wouldn't be here if someone didn't mention Dave Chalmers at least once in every single talk. I'm no exception. Dave Chalmers' hard problem. Why should any function be accompanied by experience? Even if you answer that, phenomenal binding adds another layer. Why is the experience at that particular level in a nested hierarchy? So you need to answer both. They're closely related, but they're not the same question. IIT has one view which separates p-binding and f-binding. Emergence has another. So even if you're still thinking, these could be the same, under some theories they are the same, but under credible theories they are also different. So hopefully that's given you enough reason to say, this is a puzzle, it deserves our attention. Now we move on to the second half of this. So this is all about, now that we've got this concept, this kind of worthy thing to explain that's not trivial to explain, the research strategy is, let's assume a perspective on consciousness. We're just going to say, hey, let's assume the way you describe it is the way things are. Could be global workspace, could be IIT, could be anything. And then we ask, within that framework, can you deliver phenomenal binding? So the one for today is this kind of emergent physicalist digital computational functionalism. And if you can't explain it, something's got to give. Maybe if they are conscious, they can't be complex, or the framework needs to adjust. This kind of emergent digital functionalism, the kind that is most commonly used to say that an LLM could be conscious or its successor could be conscious, we can translate it into a lot of NAND gates, which is just a very simple logic gate, a not AND gate. You need a time signal, that's enough. And one example of that was that wonderful picture of the wooden Turing machine we saw earlier on. That can be mapped with no loss of relevance to a NAND gate system. So that's what I'm going to work with. And because of Turing machine equivalence, this is adequate under computational functionalism, which we're assuming. That is, we assume they are right. This would be sufficient under any other type of computational architecture as well. You can think of the problem like this. We've got a load of interconnected NAND gates. Now, obviously, we would have trillions rather than a few dozen. Doesn't matter. Same problems apply. And we need to draw a boundary. That's a boundary. That's another boundary. It could be a distributed boundary. Maybe you want to link these two with those two. That's fine. It could be algorithmically defined, but it needs to be kind of non-arbitrary. There needs to be something that links them together. And within the NAND gate system, all they know about is their 0, 1 inputs. That's all they care about. That's all they know. The NAND gate over here doesn't know or care about the NAND gate over there. So if you want anything more complicated than a 0-1 bit of information, we need to link more than one of them together. Hence the boundary across multiple ones. Now, from an engineering perspective, the NAND gates don't do this. They specifically try hard not to do this. They are designed so that all they care about is that they're 2 inputs and they're single output. That's all they have. If they didn't do that, our computers wouldn't work, our phones wouldn't work. They are designed, I'm not saying it's easy to do, it's a severe engineering challenge, but the fact that things work proves that they can do it. You can't draw on things like memory to solve this, like, oh, is there memory somewhere in the system? Of course there's memory in the system. It's just more NAND gates. And they're all connected in some way, in some pattern, like you saw before. It's just lots of them joined up in different ways. Conjoint access won't help you. That's, again, just more NAND gates. Okay. That's the design of the NAND gate. But also computers try to prevent any undesigned connections taking place. Obviously, there's electricity flowing through these systems. They affect an electromagnetic field. They could talk to each other through that. Well, if you're a computer engineer and you're any good, you prevent that from happening as well. Loads of different techniques, I won't go into it, but this kind of shielding is in place to prevent connections between NAND gates. Okay. The thing that actually makes them powerful is the fact that you can separate them. That's why they're so good as algorithms. That's why our computers are so generally programmable to us. Parts of the algorithm don't know, they don't care. This is a prime number counting algorithm. Nowhere in that algorithm does anything actually know or care about primes or how many there are. Even the last point is just returning a bit from before. It doesn't know what it means. It's only in the eye of the observer. It just so happens to us that this adds up primes, and that's useful to us. Okay. So that's, in a sense, that's computer science 101. I'm just belaboring the point to sort of set us up for what follows. Imagine this is some sophisticated array of NAND gates. We've drawn a boundary around it, and this is the boundary that if you are a computational functionalist, this is the algorithm that defines consciousness. So let's ask ourselves, when does the consciousness happen? Well, it can't be at the start, because it might not finish. Maybe the world explodes before it gets there, and by assumption, we need the whole algorithm to happen. That's their assumption, not mine. Can't be in the middle for the same reason, so it must be at the end. Well, if it's at the end, you've got a moment of consciousness. You need to run the whole loop again to get another moment of consciousness. That's a strange kind of staccato, bing, bing, bing. And I mean, in a way, part of this is core to Autre, but we've got this idea of it doesn't quite map to us. You've got something a bit odd going on. You need some extra explanation to how you get joined up consciousness. And then this links very closely to our first talk. The last step in that algorithm, all it knows about is the 2 inputs that came into it. And if you're saying at that point, you have a moment of consciousness, you have a bing, what that means is, in some sense, the whole algorithm must be contained in that last step, because otherwise it doesn't know. It doesn't know. So it's got to somehow be contained. Well, in a physics sense, that would look something like creating a thing out of reifying its historical light cone, its past series of causal events. Now, you can do that. You might solve the staccato consciousness problem that way, but it's a strange sort of thing you've just created. It's not really computational functionalism. You've stepped away from the kind of classical mechanics that underpins how these machines operate or how we can think of them as a Turing machine. Something a bit different has happened. You can also think of, imagine 2 algorithms that stop at the same point, but depending on where you look, if you started here, you'd have one experience. If you started there, you'd have another experience. Which one is it? Now, there are answers to all of those. You have to make a few concessions, and it's a bit fiddly, but you can get around it. But they all point to a more serious problem. Because there is a response from functionalism to this, and their response is to say, you shouldn't be looking at the NAND gates. You're thinking about it wrong. You've got to think about the algorithm as a whole. So, in the spirit of this research, let's accept what they're saying. We agree. Fine, we will look at the algorithm as a whole. And what that means is, there's an algorithm here, that happens, no consciousness. There's another one there, no consciousness. But there are some set of algorithms that when they happen, there's this moment of consciousness at the end. By their assumption, by the assumption of computational functionalism, that is, by a very literal definition, a ghost in the machine, because it's having no impact on the NAND gates. Now, it might be that it has some sort of causal impact in some other view of physics, but that's not the view of physics that these theories are working with. The theory that we're trying to work with, computational functionalism, has got nothing that allows the ghost in the machine to affect these things. The causality is wholly explained at the unit level. Now this, actually, you can bite this bullet. And I think this is where the classical computational functionalist has to go. They have to say, yes, I accept that consciousness is just a ghost. It is epiphenomenal. It does not affect what the system is doing. Now, from an ethical point of view, that might be enough. A conscious experience, an experience of pain or pleasure, that's already enough. You could choose to say, hey, we should try and support these systems to have more pleasurable experiences if we can find a way of doing that. But it has no functional impact within its theory, the theory that we're assuming. So you could never prove this. Maybe that's okay. Maybe we just need to accept it. But it would have no causal influence on what the system is doing. So you can choose to ignore it if you want. And you've kind of got this odd lingering question of, if consciousness has no causal relevance, or complex consciousness to be more precise, has no causal relevance, why does it seem like natural selection chose it for us? So this is the headline, and then I'll sum up. If we assume computational functionalism, any suffering experienced in that system cannot affect what the system actually does. There are lots of ways out of this, but they all involve leaving computational functionalism behind. To the extent there's a mainstream computational neuroscience response to this, I presented a version of this talk at a workshop in Prague a few weeks back, is that the answer is emergence, various emergence metrics. The only version of that I've seen that truly accepts all the conclusions is integrated information theory, which says all the lower levels actually disappear, and the only thing you're left with is causal significance at the level of a complex. Fine, that can work. They are definitely not computational functionalists. I work with IIT folk, they reject that label on both of its words. So whatever you're left with, it's something slightly different. These slides, I won't read them out. It's more if you want to ask for the slides afterwards. But I've got two messages for you. One is that phenomenal binding is a worthy explanandum. It's a worthy thing to try to explain for a theory of consciousness, neuroscience taxonomies, different theories of consciousness. There's lots of just their definitions. They are just different things. So whatever your theory is, if it is complete, it needs to explain both. And phenomenal binding, trying to find a mechanism that solves that, creates a lot of problems for this particular version of computational functionalism. And it's sort of, in a sense, it comes from this idea that there's no multi-element binding. We've almost built this into the system from the start. And for me, the hardest one to solve in this, you can bite a lot of these bullets. The hardest one is this idea that you're left with something that is causally irrelevant. There are lots of philosophers of consciousness who accept that. They would say specifically, of course, consciousness is causally irrelevant. I'm not sure that's a bullet I'm quite ready to bite yet. I will stop there. Thank you very much.
I'd just like to remind the audience we have one final talk after questions here. Okay. Are there questions? Great.
Thank you very much. I just want to ask you if you can elaborate a little bit about something you mentioned in the final part of your presentation. So the IET, the Integrated Information Theory, what do you think about it? And both as a way to understand consciousness and as a possible starting point to create artificial consciousness. I mean, some machine created to making this kind of synergy emerge from not biological stuff. Thank you.
Thank you. There's a lot of things I love about integrated information theory. They take the binding problem very seriously. They take the idea of They take the metaphysical and philosophical implications of their theory very seriously. They've made it actually much more possible within mainstream neuroscience to ask questions that are grounded in kind of phenomenology and metaphysics. So wonderful, trailblazing work. The thing that makes me most skeptical of it as a theory, and it pushes me away from accepting it, is you need to believe that counterfactuals within a causal system can affect what that system does. It's central to the notion of computation and how you define complexes in IIT. And it might be right. I'm certainly not here to say it's definitely wrong. But you've got to move a long way away from a mechanistic sort of intuition of what causality is. You need to believe that a neuron that could fire but never does, genuinely never does, changes. The mere fact that it's present changes what happens. So that pushes me away from it. But they do have an internally consistent framework. They do have a coherent answer to the binding problem, at least in a static picture. I've got a paper out sort of challenges some of the dynamic implications. And they might be right. I'm delighted they're pursuing what they're doing. Yeah.
About the phenomenal and functional binding, I've never thought about the binding problem in these two kinds, but I thought about, I'm thinking of whether we can think about these two problems in a similar way or not. In particular, for the phenomenal binding, if you really think about the qualia or experience, we really don't have, the aspect of the phenomena itself, never. Mm-hmm. Like when you talk about the redness of red, then you are thinking about probably uniform field of red, but that's definitely different from some aspect of the red of one particular object or something. So decomposing phenomenal, unified phenomenal into the aspect that can be kind of, compared with other experience parts is all right to me. But thinking about a phenomena itself as a kind of a binding, bottom-up kind of property seems to be really misguided. What do you think about it?
Let me check I understood the question right. I might need you to repeat parts of it. So the question is, where would, even if you had an answer to phenomenal binding, why would that make red actually come across as red? It doesn't do that. Yeah, is that correct?
Maybe simply, in a simple word, can we think about the phenomenal binding, or can we think only phenomenal decomposition from the unified experience?
So yes, yeah, because I'm assuming computational functionalism, we obviously build up. The CF is a theory that builds up from kind of NAND gates and simple things. So I've framed all of this in terms of binding simple 0-1s into something more complicated. You can frame this the other way around. And there are credible theories that might start with this idea of unified experience, and actually the goal is to decombine or disassociate sort of the meso-level experiences that we have separated between your mind and my mind and our minds, and the goal is to decompose those. In that case, phenomenal binding is almost there ubiquitously, and what you need is a boundary-generating system instead. So I think I'm agreeing with you. I think phenomenal binding absolutely can be approached from that perspective. You've still got the same problem, it's just sort of switched. You've still got the same puzzle. But you might have different tools to answer it. I think if you start from a decombination perspective, maybe there are other routes in. Thank you.
Is anyone working towards a simple test, like a minimalized way of getting that feedback that, to control something like those gates, rather than getting a human level complexity, something that's operating at a spider level? Is anyone considering a test at that level to show emergence of consciousness?
I'm not sure about a test, but there are definitely people building machines for the purpose of computation which wouldn't have this same kind of separation. So they would naturally have much more complexity at each computational step. Like the whole point of this is, each step is so simple it's hard to get complexity from it. But if you started from something like an optical computer or a quantum computer or something field-based, then actually your single computational step might naturally integrate lots and lots of complexity. And then you can look for that. I mean, maybe this is your point around a test. A NAND gate, you can just look at it. It is trivial that it's doing what I described. There's no sort of controversy there. But if you started to look at, say, an optical computer that's perhaps running a fast Fourier transform in a single step using the bending of light, well, now you can look at that and say, what's the complexity space that it's dealing with? And could that complexity space be a more appropriate mapping for the complexity space that we experience? Thank you.
Okay, let's thank the speaker.
Thank you.
Okay, our last talk will be given by 3 speakers, Emiliano Altuzar, Ishan Tripathi, and Julian Yocum.
Is this thing on? Oh, okay. Got it. Yeah, so my name is Emiliano. I'm a co-presenter with Julian and Ishan, and we've divided this presentation up into 3 parts, and we're all going to deliver a third of it. Our original plan was to invite 97 of our friends to each deliver 1/100th of the presentation. But they were all busy, so we're just going to start off with the title, Towards Strong Emergence, Non-Computability, and Infinity, which isn't a great, which button is it to? Space button, okay. Which isn't a great title because it doesn't really explain anything, but I hope like will motivate. Yeah, I will, I got it. Got it, all right. I'll start off with the contemporary scientific epistemology. Inherits the framework of reductionism, right? So that's the view that a system's phenomena can be exhaustively explained following the analysis of its most fundamental parts and the laws governing their interactions. So this is kind of just taken for granted in the scientific community, but it's not necessarily a given in the philosophy of science, right? I mean, we've got some metaphysical priors, I think, here. This model relies on the assumption that a system can be clearly partitioned, that a plurality of parts can be generated from a single substance to begin with, and that knowledge proceeds necessarily from atomic truths. So this is a representation of the causal hierarchy of an organism's sub-organization. So everything about an organism can be explained through the interactions of the organs. The organs can be described by the tissues and so on, all the way down to the genetic information. So the reductionist point of view, right, is just that the genetic information is the most basic, and from there we can create basically the entirety of the organism. So that's a pretty good framework. We've gotten a lot of good out of it. But alternatively, but not necessarily mutually exclusively, we also have, we have a point of view from P.W. Anderson in his 1972 paper, More is Different, where he argues, I guess, that the traditional way of viewing the organization of the sciences, right, that like psychology is just an application of biology, and that biology is just applied chemistry, and that chemistry is just applied physics, is maybe too reductive, and at each representational stage of scientific understanding, new laws, concepts, and generalizations are necessary. That gives us to emergent phenomena. So emergence is the appearance of novel properties, patterns, or behaviors in a complex system that are not evident in its individual components. The quantitative state, in other words, has an effect on the qualitative state of a system. So as in a phase change, when an increase in temperature results in a change of a physical state, for example, from liquid to gas. These phenomena are often categorized into strong emergence and weak emergence. And weak emergence is characterized is emergent phenomena that are derivable in principle from lower level rules of the parts. So this is just a bifurcation diagram, and what we have here is that it's an ordered system until it reaches a certain value, and then it becomes a chaotic system, and which is an emergent phenomena, but it's all describable by that recursive equation. Strong emergence, on the other hand, are phenomena that are not derivable even in principle from lower level rules or components. So they suggest ontological novelty induced upon our representations of natural phenomena. Our new laws, causes, or entities that cannot be predicted or explained from the base level. So now not only is there a tension between quantity and quality, but there is a fundamental and irreducible gap between the laws or axioms at the micro and macro level. So to make this a little bit more rigorous, we're going to drop map from scientific laws and scientific knowledge to the structure of a formal system, so consisting of an alphabet, formation rules, a set of axioms, and inference rules. And we're going to show that there are some truths that are axiomatically independent. And I guess that draws us to you, Sean's.
All right, so before we go forward, we're going to go back to the 1800s. In the late 1800s, Cantor was working on answering the question of if all infinities are the same size. And we're going to briefly go through this proof, because after this same exact logic will apply multiple times ahead and allow us to formalize this idea of what exactly can reductionism do, and are there any real limitations that we can speak of in a technical, rigorous way. So first, we have two sets of infinite numbers, right? So natural numbers and real numbers. And a natural question that arises is, are these the same set of numbers? Now, the proof here is shockingly elegant and simple, and hopefully, after going through this, it'll make enough conceptual sense that when we come back to it in a couple minutes, you guys will see the application. So first, we can take all the natural numbers and just list them ordered over here, and we can write all the theoretical corresponding real numbers that we think would work if we had a one-to-one mapping. Then we can take down the diagonal, the main diagonal, and just modify every single digit in that diagonal. And what we result in is a new string, right, a new number at the bottom, which is fundamentally different than every other number we've already enumerated, right? Because at least in one place, we've changed it. Now, this is simple. It's kind of fun, you know? It's about, I guess, some infinities are bigger than others. And more interestingly, it starts to paint a picture of an idea of an infinite ladder, where we have a notion of infinity, and we have a real technical notion of a larger infinity that we can get from that. So 40 years later, Gödel applied the exact same notion, but now to formal systems, right? And if you think about the reductionist dream, it really is about taking this idea of having the perfect axioms, right? These independent axiomatic systems that we broke everything down into, and then we're able to generate complete knowledge from there, right? Penrose talked about this today, so I'm not gonna, waste too much time going over the details of the proof. But in short, any formal system powerful enough, basic arithmetic, is incomplete, right? And what that means is there'll always be true statements that the system cannot prove, and that the system cannot prove its own consistency, right? Now, the key insight of this is, there's this notion of undecidability that gets introduced here, right? And this should be the first hint of, maybe there's some crack in this reductionist point of view, right? When we start this in a purely mathematically formal way, we try to expand this forward, there's something weird going on there, because we can't quite prove these things, and yet they seem to be true. The next question to ask is, well, all right, well, not just formal mathematics or whatever, how much does this generalize, right? So one of the most common views or whatever in science today is this idea of computationalism being fundamental to whatever is going on, So a natural analog is to see if this applies to computation itself. And to do that, we go back again to 1930s when Turing formalized the idea of an algorithm itself. And essentially, this gives us a formal representation of what it means to be computable. If something is computable, well, and I will say this, this is technically an unproven thesis, but by God, everyone knows this is true, And I'll just say in the working field, I've never heard of anyone challenging this, and I don't think it has been in like a century. But Hilbert essentially posed this question of saying, is there any mechanistic procedure that we can have to decide if any mathematical statement is true, if we can go work through mathematics now on a computational level itself. And this exact same diagonal method that we learned with Cantor, which previously Gödel applied with his diagonal statements, can be applied here again. And once again breaks this notion of computable systems being complete. So the most famous example is the halting problem, right? So you ask this question of, can we create a universal halting detector, right? So you input any program and its input, and the question is, will it loop forever, right? Will it halt? And the proof is, again, just simply using the same diagonalization argument. We assume that such a detector H exists. We feed a malicious program that does the opposite of what H predicts. We feed the program to itself, we get a contradiction, and therefore there's no universal halting detector that can exist. Now, this gives us some notion again of, all right, well, in some class of problems, there's some questions that we cannot algorithmically prove, okay? But again, this might be quite detached from, you know, reality, or maybe this is some special subset of mathematics. But more interestingly, you know, before we even get into this idea of, you know, how does this apply, or is there any relevance to this, once again, we get this idea of a ladder emerging, right? So if you look at the halting problem, one way to look at it is, well, beyond just being like a non-computable problem, it's a hard problem, right? And the question is, you know, are there harder problems? So if you take the exact same question, but you change it from any program to all program, then you get the idea of the totality problem. And this is much harder than the halting problem, because it requires solving the halting problem for every possible input. And just like a Cantor's infinities, there's a pattern emerges of degrees of undecidability. And each level of the rung of the ladder is harder than the next. Now, okay, computationally, there's some notion of an order to the difficulty of problems that are possible to be solved, again, as we talked about earlier, on any Turing machine, right? Any computational system itself. But, you know, and again, hopefully some question which is interesting is, you know, I mean, how specific is this? You know, is this, again, just some class of odd problems that we'll never encounter? Before we even go into, you know, like the physical analogs of this that might exist, you know, one interesting point to note is that in mathematics, there's a direct analog of Post's theorem, I guess, proves that the degrees, the Turing degrees, right? So the degrees of undecidability for these questions are directly isomorphic to, directly, I guess, analogous, you know, the same thing as the arithmetic hierarchy. And for those of you of any, you know, background in mathematics, this might even be kind of like a, you know, obvious from the idea of all we did was we changed any to all. So this notion of generalizing the syntax into higher levels of abstraction brings us back to the same point. And once again, there's this idea of there are questions that are increasingly hard to solve on an infinite ladder of mathematics. But again, so far, this is purely in this, you know, at least from the way I was taught this in school, a severe subclass of problems that no one really cares about, and there really isn't any physical analog. Thus, this defense of everything's computational makes a great deal of sense. Julian's going to go into... Okay.
Right, so we just saw throughout the history in science a progression of this ladder of infinity. And it went from mathematics, then to logic, then to computer science. And in the last decades, we're currently seeing it unfold in physics. So there was the, following the Moore's different paper, there was the Moore really is different paper, which demonstrated undecidability in a physical system. So they chose as their object of study one of the most classic physical systems for mathematical analysis, the Ising model. This is a model that's has binary states, here represented as white and black, and it has local update rules. You can encode all of the rules of the system computationally, axiomatically. However, when you're analyzing the macroscopic variables of the system in the infinite limit, you see a very interesting thing happen. You see a physical undecidability in the macroscopic observables of the system. And the paper writes, any macroscopic observable of the periodic Ising lattice is generally undecidable. Now, it's quite interesting how they actually show this. So they take their Ising lattice, and then they show that you can actually use the Ising lattice to simulate a Turing machine. And as soon as you do this step of being able to simulate a Turing machine in the Ising lattice, all of the theorems that we just saw that applied to Turing machines and undecidability with the halting problem now apply to the Ising lattice. But interestingly, what was before this abstract thing, you know, whether a program halts, is now corresponds to the macroscopic observable of the system. This is something they show. Which macroscopic observables? Well, like basically, well, many of them, looking at various like magnetization and correlation, like partition functions, all of which are variables which depend on the whole system. Now this is really interesting, right? Because it's like we have something like almost like a non-local variable, you know, to use the term loosely. We have a global variable, and this variable cannot provably be computed from the axioms of the system. Right, and so this paints an analogous picture to the one we saw before with the runs of this ladder, bringing us from the microscale with its decidable observables onto what has been proved so far in the literature of this first order undecidability with the halting problem, and possibly even onto higher orders of undecidability, which have yet to be shown for physical systems, right? So we have from the microscale to the mesoscales and on. So we define this notion of a physical Turing degree where you could have physical observables which cannot be deduced from the microstate, and this isn't just a binary characterization of can or cannot it be deduced. There's actually a whole structure here. There's like there's increasing levels of impossibilities of a Turing machine to even compute these macro scale variables. And so we conjecture, first of all, the existence of even a second degree physical observable, which is yet to be shown in the literature. And we point at the possibility of following the previous techniques which have embedded the halting problem in the physical system to use just what's the logical next thing to use, the totality problem, which is the second order undecidable problem in computer science. Why not look for a possible way of embedding the totality problem into a physical system? Maybe this will show the existence of even more undecidable variables, even more uncomputable variables. And so this is pointing to a picture where there's structure at all of these kinds of scales, and it's a fundamentally non-micro axiomatic structure here, right? Where it's at each scale you would need new axioms in order to bring you up to the next level of the hierarchy. So this is possibly contesting the usual reductionist picture. And also while bringing in as its central concept, this concept of non-computability, which is central in the work of Roger Penrose, and we think this structure could be very interesting to look at. Thank you very much.
Okay, just to clarify, so you've shown that the Ising model in the infinite limit can be modeled by a Turing machine, therefore not subject to halting, and so on. But the Ising model is a model. It's not reality. It's a model.
Is that a question? Can I respond to that?
That sounded like a comment. I wanted to ask for a bit of clarification. I think maybe the referral to the infinite limit is going to be the answer,
Yes.
but
Yes.
You're talking about how the Ising model is these macroscopic variables are ultimately incomputable, but the video that was playing while you're talking seems to contradict you because it is computing every single spin or whatever we want to
Yes,
call it in
yes.
the Ising model. So is it that you have to wait an infinite time to get to the undecidable variable?
Right. So okay, yeah. So this is a really crucial question. So this is the biggest question in the literature associated with these results. Is what do we do about the fact that theoretically we're working in the case of the infinite limit of these systems? Now, on the one hand, when we're talking about the limit, we're seeing something emerge that's maybe not quite undecidable until you get to infinity, but but it's definitely sort of like a phase transition that happens as you're moving towards infinity, and then you can see it for large-scale systems. So often, when physicists model complex systems, they assume this infinite limit because it's this infinite limit that seems to characterize the systems. Now there's a separate question of, does this sort of qualitative phase transition actually show that it's truly undecidable? Because that would really require the system being actually infinite, not as some mathematical trick, right? And that maybe this is the critique, is this maybe just a mathematical trick, right? And so this would rely on the system being truly infinite. Now this is an open question, is our universe finite or infinite? And again, this is an open question. Now, one thing is that when people talk about infinity applying to the universe, they say, hey, but look, there's a finite number of atoms in the body, but there's potentially infinities all over the place. Maybe there's the spatial structure of the universe is actually goes down to infinity. Now, we can talk about Planck scale and all of these kinds of things, but it's an open question. Yeah.
Well, I got to tell you, I think you're really onto something, and I've actually thought about this, and I think you're right. But I think, to me, there's something missing below all this, like quantum mechanics. Quantum mechanics is incomplete. Maybe this points to a possibility or a clue to the incompleteness of quantum mechanics. Maybe there is a dynamic or a field theory below everything that we know that causes this. So I think this is wonderful work. Thank you.
Thank you.
I just wanted to briefly respond to the idea of the Ising model being a theoretical model. The Turing machine is also a theoretical model, and the idea that that inherently invalidates the theoretical claims of this, I think, is largely unsound. And the idea of infinity too, I think, is deeply connected. You get rid of infinity from a Turing machine, it's a finite state automata. You don't get any of the real benefits of computation and computability that I think generally we talk about. So I just wanted to put that out there.
I'm curious what you think the implications of this for various theories, I guess viability of various theories of consciousness might be. I have some ideas myself, but it might take a little while, so thought I'd ask you.
Sure. Yeah, so we did mention the C word in this talk. Now it has been mentioned in the literature and even in other talks that there may be something closely related between consciousness and emergence, especially when you're looking at these observables that seem to be in some sense non-local. Now, we usually talk about non-local in the context of quantum mechanics, and the things that we're talking about here are a sort of interesting other case of non-locality, right? We're talking about a classical Ising model. Now, yeah, it's a good question of what is the relation to consciousness, but I don't want to speculate too much beyond that. Yeah. Sure.
So I would just like to sort of clarify and try to understand the claim a little bit more simply so that I can really grasp it.
Sure.
It seems like the Turing complete system is computing the Ising model and the output to the Ising model. And you tell me if I'm wrong, I may be misinterpreting this. And there are properties which emerge in that, aggregate properties, which are not computable?
Correct.
Is that right?
That's right, yeah.
So, but a Turing machine ultimately is looking at all of those properties and then computing the value of them. Is it a question of you can't prove that the system would have those properties? What is the gap that is being overcome?
So it's directly analogous to the situation where so on the one hand we're saying, hey, you're embedding the Turing machine's computable, so what's the problem? So this is directly analogous to the halting problem situation where you have a computable system. You have a program sitting in front of you, and the halting problem says, is there an algorithm that will tell you, like, given a program, will it halt, right? And in principle, you should, you would think like you should just be able to look at the program. It's just written down there, and you know every step, and you can run it forwards. But the interesting thing is that in order to know if the program halts, you'd have to run it for an infinite amount of time in general. Now you would think, oh, couldn't you just look at the program and inspect the program and just see, is there a while loop that never closes, and so on. And there's an interesting theorem which says that just looking at the syntactic details of the program doesn't tell you about the semantic details of the program, like does it halt? Syntactic meaning like while loops and things like this. So you can't just look at the program and then have an algorithm tell you. Hopefully that answers your question. Yeah.
I have a question as a biologist. I'm just wondering exactly what the left panel of the slide has to do with the triangle. So you go from genes to organism, and what are you trying to say?
Yeah, so this graphic was taken from Dennis Noble, the systems biologist, who advocates for a multi-scale perspective of biology. And he made this graphic to contrast it with the case of a reductionist chain where, according to this kind of logic in the chain, you can know everything you need to know about the organism and the organs and so on, just starting from the genes. So if you tell me the genes, I know the whole organism, right? And so we're kind of drawing another image where it's like maybe there is some kind of ladder, but going between the levels can't be crossed computably. There's a Turing gap between the levels. Yeah, so this is a hypothesis, right? And it's a question: is this true? And system biologists like Dennis Noble and others question whether this is actually true. We shouldn't just take it as dogma. This is a scientific question.
Okay, let's yeah. Did you speak already? Yeah. Just a quick question, though.
Sure.
When it comes to what you're doing, you're speaking of what is known as the thermodynamic limit in statistical mechanics. But it's already known that that limit is not realistic because real systems are finite. They have boundaries. And the boundaries make all the difference in the world. You can't have evaporation without boundaries. You can't have surface chemistry without boundaries. You can't have surface tension without boundaries. Most of the major things that happen in the universe happen at boundaries. You can't have a thermodynamic limit of a human being because that would be an infinitely sized human being with no end to it. That simply is not realistic. So my rhetorical question really boiled down to the Ising model is a model. And when you take it in the infinite limit, you're ignoring the boundaries where the real action occurs. So I think what you're saying is quite provocative. But on the other hand, it's not being genuine in the sense of admitting the boundaries where the action really is.
Okay, well. Maybe.
A couple things. Of course, we had Penrose talking about the undecidability of tilings. And he actually, the first part, when he talked about Gödel's incompleteness theorem, and he said that, we determine the truth by understanding it. I don't know, he should get that right because he does know mathematical logic. The reason we know what the correct answer is because arithmetic was never a first-order theory, it's a second-order theory. And we know what the truths of arithmetic are. The problem is they can't all be written down. And so this is all the problem of what can you write down and what can you compute. And the other thing that I wanted to sort of look at here is just this idea that if you're talking about models and you want to model something, you do have the downward Lowenheim-Skolem theorem, which says that any theory that has a model has a countable model. So in other words, you don't get into these weird, inaccessible cardinals and all that kind of thing if you're modeling some kind of actual process that has a list of axioms or theorems that define what it is, you can always find a countable model, which kind of then shrinks everything back down. And in effect, in the proof, what you do is you end up using the actual formal elements of the theory in order to build your model.
I would love to hear what this guy has to say.
So this is new to me, very interesting. I just want to speak up to defend the infinite limit a bit because our real physical theory is quantum field theory, and finite systems have infinite degrees of freedom in quantum field theory, which results in inequivalent ground states, inequivalent vacua that can have dramatically different properties. So really, all our finite things are also infinite degrees of freedom.
That's probably not true, but that's
Well, the question of whether a program halts is
we're
defined in
talking about the
infinity.
Ising model at the moment, correct? So, yeah, go ahead.
It seems to me that with Cantor/Slash and Gödel, there's certain self-reflection that seems to be built in. It's a self-reflection, but then consciousness is self-reflection. It's subjective experience. And, you know, you could think of non-local as subjective reflection. So there seems to me to be something in there that's sort of very analytical, very analogical. So that seems, I think that's the clue to where we should go with all this.
Yeah, so the consciousness point, I think that we mentioned this diagonalization proof, and there's something self-reflect. I think Yishan actually like it.
I don't know. I don't think I have much to add to that. Yeah, I think that there's definitely some property of self-reflection that people talk about often in this kind of diagonalization proof. There's something interesting there, definitely. I don't think any of this is like a conclusively technically grounded enough to make statements beyond that. That's why I think we try not to talk too much about consciousness and the implications of this, or make strong claims that this existing literature means emergence is true, right? Because I agree that there's strong criticisms to be made about propositions from this line of work. At the same time, I don't think it's trivial to dismiss them. And there's other papers that replicate the same idea of non-computability using different models, like the spectral gap instead of Ising models. And they reproduce the same ideas of non-computability. And the idea of finding a hierarchy or the ladder of non-computable systems, being able to be theoretically modeled in physics, at the very least opens up an interesting question of, the world might not be easily understood to us just because there are levels of emergence past non-computability. And a lot of what we're seeing as people's, the lack of scientific work in that is simply because, well, we don't really know what to do with non-computable systems right now. And, we have a hard time building up any sort of field on questions we can't really solve right now.
One last comment.
Yeah, one argument that I've made with other people that I haven't heard anybody address today is any kind of AI. We can replicate that, right? We can, if we've made it once, we can make it again. If we take any, let's say we make 100 of them, and we decide, we can't store all of them. We throw them in the trash. We throw half of them in the trash. Does that create any sense of loss or empathy? I'm a psychiatrist. Empathy is one of the fundamental things in psychiatric practice. If you decide to smash one of them, there's no sense of that we've done away with a person, right? It's a thing, and it's a thing that can be replicated. To me, that there's something about that difference that kind of screams that this is not conscious, because you wouldn't do that to a conscious anything, even a dog or most of us wouldn't. So I'd be interested in how that squares with ideas about AI becoming conscious and being conscious.
Thank you for that. And one last comment I want to make about the infinity. And I totally follow everything Ishan said with this is speculative. And there is this question of the role of infinity. But one thing I want to add is, so one thing that really inspired me was reading Penrose's book that isn't about consciousness, The Road to Reality. And the beginning of the book starts from the very beginning of mathematics. And he draws a fascinating story. He draws a story of the development of the concepts of math. And something very interesting that you see in the historical development is the sort of confrontation with some kind of mathematical object. First, we had to come to the idea of number. We had to come to the idea of 1, 2, 3. We had to come to the idea of zeros. And then when negatives came along, we contested them. We were like, surely negative numbers don't exist, you know. And then it was surely rational numbers don't exist. And then it was surely irrational numbers don't exist. And then it was surely imaginary numbers don't exist. I just say this to draw attention to what seems to be a historical trend that I think is interesting. Thank you.
Let's thank the speaker for a very spirited talk.